You're standing at the edge of a forest, and there is no path in front of you. Not a faint one. Not an overgrown one. None. The trees go on in every direction. Identical, indifferent, and somewhere behind you, the light is starting to fail. You have nowhere to check a map, because no one has ever drawn one. You have no signs, no painted lines, no GPS pin blinking your location back at you. Every direction looks exactly as plausible and exactly as dangerous as every other one. Now open your eyes. You're probably indoors. There's a road outside, paved, lined, lit, leading with total confidence to 100 other roads that eventually connect to almost anywhere on Earth. You didn't build any of it. You've probably never thought about who did. For roughly 300,000 years, humans lived without a single mile of constructed road. No gravel, no cobblestone, no worn dirt track cut by engineers. And yet people still managed to trade obsidian across 1,000 miles of desert, follow herds across entire continents, and find their way home in the dark. So how did ancient humans actually move through the world before roads existed? And how did they do it well enough to spread across every landmass on Earth without ever getting permanently, fatally lost? The honest answer starts somewhere you wouldn't expect. Not with humans at all, but with animals. Long before a single person deliberately cleared a route through the wilderness, other species were already doing the engineering. Elephants in Central Africa carve paths through dense forest that are so consistent, so repeatedly reinforced by generations of the same herds walking the same line, that modern satellite imagery can pick them out from orbit. In 2018, researchers publishing through the Wildlife Conservation Society mapped elephant trail networks in Gabon's Lop National Park and found that many of the routes had been in continuous use for so long they'd compacted the soil into something closer to hardpack than forest floor. A grown forest elephant weighs somewhere around 6,000 pounds. Every one of those pounds pressed into the same 6 inches of ground, thousands of times a year, for centuries. That's not a trail by accident. That's a trail by sheer repetition. Early hominins didn't invent the idea of a path. They inherited it. The first roads humans ever used were the paths worn by the animals they were tracking. Game trails that already solved the hardest parts of the problem, where the water was, where the low mountain passes were, where the ground didn't flood. Following an existing trail wasn't a shortcut. It was survival math. Why resolve a route-finding problem that a herd of megafauna had already spent generations solving for you? So what does that actually look like on the ground? Here's where it gets specific. In 1999, geographer and hominin migration researcher Christy Turner, working from data compiled at Arizona State University, helped popularize what's now a widely cited idea in migration archaeology. Early human dispersal routes out of Africa and across Eurasia don't look random on a map. They cluster along corridors that match known megafauna migration paths and coastal shelf edges, the lowest energy, lowest risk routes across a continent. One especially telling number: the primary route thought to have carried early modern humans along the southern coast of Arabia and into South Asia runs almost entirely below 500 meters of elevation, hugging the coastline for thousands of kilometers. Even where a straighter inland route existed, humans weren't choosing the shortest path. They were choosing the path that minimized the number of ways they could die between one water source and the next. Everyone assumes that ancient people wandered wherever curiosity took them, chaotic and unplanned, the way we picture cavemen bumbling through an unmapped world. The truth is closer to the opposite. Long-distance ancient movement was some of the most rigorously optimized behavior humans have ever engaged in. Because the penalty for getting it wrong wasn't inconvenience. It was death by exposure, dehydration, or a large predator that also knew exactly where the water was. That optimization gets even stranger once you leave land behind entirely. In 2017, a team led by archaeologist Sue O'Connor at the Australian National University published dating evidence from Madjedbebe, a rock shelter in Australia's Northern Territory, pushing back confirmed human presence on the continent to at least 65,000 years ago. That date matters for one specific reason. To get to Australia at that point in history, even during the lowest sea levels of the last ice age, people had to cross open water, not a narrow strait you could see across. Water gaps of 70 to 90 kilometers in multiple stages, with no landmark visible on the far side for most of the crossing. There was no coastline to hug. There was no game trail floating on the ocean. So what replaced the path when there was no path to follow? The answer, most likely, is the sky. Modern experimental archaeology has tried to reconstruct what that crossing might have taken. In 1998, a replica bamboo raft expedition led by archaeologist Robert Bednarik attempted to cross from Southeast Asia toward Australia using only technology plausible for the late Pleistocene. no metal, no modern navigation. It worked, but barely, and it revealed something important. Without a fixed star position and a working mental model of drift, current, and dead reckoning, the raft would have missed the continent entirely. A 3-degree navigational error over a 90-kilometer crossing is the difference between landfall and open ocean forever. 3 degrees. About the width of your fist held at arm's length against the horizon. That's the entire margin ancient navigators were working inside. This is where the idea of the road starts to fall apart as the right way to think about ancient movement at all. A road is a fixed line scratched into the earth. What early humans were actually building, wherever they went, was something more like a fixed line scratched into memory. Nowhere is that more extreme or better documented than in the wayfinding traditions of the Pacific. In the mid-1970s, a Micronesian navigator named Mau Piailug from the tiny island of Satawal sailed a reconstructed double-hulled canoe called the Hōkūle'a over 2,300 miles from Hawaii to Tahiti with no instruments, no compass, no sextant, no charts. The voyage, documented by the Polynesian Voyaging Society and later analyzed extensively by anthropologist Finney, took 34 days. Piailug navigated the entire distance using a memorized mental almanac of roughly 220 stars. Their rising and setting points on the horizon, plus wave patterns, swell direction, cloud formations, and the flight paths of specific seabird species that reliably signal land within roughly 30 miles. 30 miles, across an ocean that stretches for thousands. That's the resolution ancient Pacific navigators were working at, without a single piece of modern equipment. A resolution some modern sailors struggle to match with GPS turned off as a training exercise. So how do you even begin to hold that much information in your head? The honest answer is, you don't hold it as facts, you hold it as a story. This is the part that tends to surprise people most, because it inverts almost everything modern life has taught you about what a road is supposed to be. In Aboriginal Australian cultures, some of the oldest continuous cultures on Earth, there exists a navigation system that doesn't use maps, doesn't use written directions, and predates the wheel by tens of thousands of years. It's known in English as Songlines, although that translation flattens something much more precise. Anthropologist Norman Tindale spent decades, starting in the 1920s and continuing into the 1960s, working with Aboriginal communities across Australia to document these routes, eventually mapping hundreds of distinct song cycles tied to physical landscape features across the continent. A songline is a chain of landmarks, a rock formation, a waterhole, a particular tree, a bend in a dry riverbed, encoded into a song. The song has to be sung, in order, in the correct sequence, to remain accurate. Skip a verse, and you skip a landmark. Get the order wrong, and the map collapses into nonsense. Some documented songlines stretch for over 1,000 kilometers, crossing what are today several Australian states, passed down accurately for what genetic and linguistic dating research increasingly suggests could be thousands of years, with some researchers, including linguist Patrick Nunn, working with University of the Sunshine Coast colleagues in the 2010s, arguing that certain Aboriginal oral traditions may encode geographic and coastal information dating back over 7,000 years, correlating with sea level changes that occurred at the end of the last ice age. Read that again slowly. A road built from memory, encoded in rhythm and melody specifically, because rhythm and melody are two of the most durable things the human brain knows how to store, outlasting almost every physical monument humans have ever built. The pyramids at Giza are roughly 4,500 years old. Some songlines may be older than that by a factor of 2. So what happened when humans actually did start cutting physical paths into the earth? Not just memorizing routes, but building them. That's where the story shifts from cognition to construction, and it starts far earlier than most people assume. In 1970, archaeologist John Coles began excavating what's now called the Sweet Track, a wooden causeway found preserved in the peat bogs of the Somerset Levels in England. Using tree ring dating, Coles and his team were able to date the timber with extraordinary precision. The track was built in the winter of 3807 to 3806 BCE, not around that date, that exact winter, because waterlogged wood preserves growth rings well enough to count them almost like a calendar. The Sweet Track ran nearly 2 kilometers across marshland that would otherwise have been impassable, built from split oak planks pegged into the mud on a timber frame. 2 kilometers of engineered, planned, deliberately constructed walkway built almost 6,000 years ago by people with no metal tools beyond flint and bone. This wasn't an animal trail people happened to walk along. This was infrastructure. Someone looked at an unusable wetland and decided the correct response was to build a road across it. Everyone assumes road building starts with empires. Rome, in particular, gets credited as though it invented the concept from scratch. The truth is that by the time Rome built its first paved road, the Via Appia, starting in 312 BC, humans had already been engineering deliberate travel infrastructure for well over 3,000 years. Rome didn't invent the road. Rome scaled it, standardized it, and paved it, turning a good idea into an empire-spanning system. That said, the scale Rome achieved is genuinely staggering, and worth sitting with for a moment before moving on. At its height, the Roman road network stretched to roughly 250,000 miles, according to estimates compiled by historian Ray Laurence in his research on Roman infrastructure, with about 50,000 of those miles paved to a hard all-weather standard. To put that in a number you can actually picture, 250,000 miles is enough to circle the Earth 10 times. It connected a territory covering roughly 2 million square miles, and it let a message or a legion move at speeds, up to about 50 miles a day for military units, faster for dedicated couriers using the Cursus Publicus relay system, that Europe wouldn't see matched again for well over 1,000 years after Rome's collapse. But there's a problem with treating Rome as the true starting point of the road story, and it's a problem most documentaries about ancient roads quietly skip over. So, was Rome really where the sophistication peaked? Here's where it gets strange. The most technically sophisticated road-building tradition in the pre-modern world may not have been Roman at all. It may have belonged to a civilization most people have never heard, called road builders in the first place, the ancestral Puebloans of Chaco Canyon, in what's now New Mexico. In 1971, archaeologist Chris Kincaid, coordinating a National Park Service survey program, began systematically documenting what's now called the Chaco Road System, a network of arrow-straight engineered roads radiating out from Chaco Canyon, some up to 30 feet wide, cut through solid rock in places where a footpath would have worked just as well. Aerial and later LiDAR survey work through the 1980s and 1990s, published by researchers including John Roney and Michael Marshall, confirmed over 180 miles of these roads, some running for over 40 miles in a completely straight line, deviating from true geometric straightness by less than 1 degree, regardless of terrain. That last detail is the one that matters most. These roads don't curve around hills. They go straight through them, straight over them, cut directly into cliff faces with carved stairways, where a curve would have been dramatically easier to build. The ancestral Puebloans, working roughly between 850 and 1250 C, had no wheeled vehicles, no draft animals capable of pulling a cart. The roads weren't built for transportation efficiency in the way Rome's were. Modern archaeological consensus, including work by anthropologist Stephen Lexon, increasingly favors a ceremonial and cosmological explanation. Roads built to align with sunrise positions, cardinal directions, and sightlines between distant great houses, functioning less like highways and more like the songlines of Aboriginal Australia turned into physical stone. A spiritual map you could also, incidentally, walk on. So what does that tell you? It tells you that the assumption most people carry, that ancient roads were always built for the boring, practical reason of getting from point A to point B as efficiently as possible, is wrong more often than it's right. Roads meant something. They still do. You just don't notice it anymore, because yours were already there when you were born. There's a similar story half a world away, in the Andes, and it involves numbers almost too large to process comfortably. The Inca road system, known as the Hōkūle'a, is estimated by researchers working with Peru's Ministry of Culture and UNESCO's 2014 World Heritage documentation to have covered somewhere between 25,000 and 40,000 kilometers. Built and expanded primarily during the 15th century, in less than 100 years of concentrated construction under a succession of just a few rulers. It ran through the most vertically brutal terrain on Earth, the Andes mountain range, with roads climbing to over 5,000 meters above sea level, well above the altitude where most unacclimatized humans start to experience the early symptoms of hypoxia. The Inca had no iron tools, no wheel in practical use, no draft animals beyond llamas, which can carry maybe 25 to 30 kilograms each, a fraction of what a horse or ox can pull. And yet they built a continuous network capable of moving a message roughly 240 kilometers a day, using a relay system of trained runners called chasquis, stationed in small waypoint huts spaced a few kilometers apart along the route, close enough that a fresh runner was always within sprinting distance of the next handoff. 240 kilometers a day, on foot. Across mountains. That's genuinely faster, point to point, than the Pony Express managed on horseback across the American plains almost 400 years later. A fact that tends to make people's eyebrows go up the first time they hear it stated plainly. So here's the reset question worth sitting with for a second. If humans could build systems that precise, that fast, that far, in 3 completely unconnected civilizations, Rome, Chaco Canyon, and the Andes, without any of them knowing the others existed, what does that say about the drive behind road building? Is it really about the pavement? Or is it about something older than any specific technology, the raw, non-negotiable human need to make distance predictable? That question gets even more interesting when you zoom back in, from empires to individuals, because most people, for most of human history, weren't traveling on Roman highways or Inca relay roads at all. They were traveling exactly the way the very first humans did, alone or in small groups, with nothing but memory, environmental reading skills, and a genuinely remarkable piece of internal biological hardware. Here's the twist most people don't expect. Some of the most important road building in human history didn't happen outside the body at all. It happened inside the skull. In 1971, neuroscientists John O'Keefe and Jonathan Dostrovsky, working at University College London, discovered what are now called place cells, individual neurons in the hippocampus that fire in response to a specific location in space, essentially acting as a biological GPS coordinate stored directly in brain tissue. In 2005, a related discovery followed from Edvard and May-Britt Moser at the Norwegian University of Science and Technology. Grid cells, neurons that fire in a repeating hexagonal pattern as an animal moves through space, functioning almost like an internal coordinate grid laid over the environment. The work was significant enough that O'Keefe and the Mosers shared the Nobel Prize in Physiology or Medicine in 2014. What this means, in plain terms, is that the human brain didn't evolve to need roads. It evolved to build its own internal ones. Every time an ancient forager walked a route to a water source and back, their hippocampus was quite literally laying down a physical cellular map. Not a metaphorical one, a real structural change in brain tissue, dedicated entirely to remembering how to get somewhere and back alive. There's a striking piece of comparative evidence that makes this even more concrete. In a widely cited 2000 study published in the Proceedings of the National Academy of Sciences, neuroscientist Eleanor Maguire and colleagues at University College London scanned the brains of London taxi drivers, people required to memorize roughly 25,000 streets and thousands of points of interest within a 6-mile radius of Charing Cross, a training process known as the knowledge that typically takes 3 to 4 years to complete. The scans showed that experienced taxi drivers had a measurably larger posterior hippocampus than matched control subjects, with the size of that brain region correlating directly to years spent navigating the city. Modern taxi drivers, memorizing a modern city, were quietly reproducing the exact same neurological adaptation that let a Polynesian navigator memorize 220 stars, or let an Aboriginal songline carrier retain a 1,000-kilometer route across a continent. Same biological mechanism, same brain structure, doing the same job it's been doing for roughly 300,000 years, regardless of whether the road in question is made of stars, songs, or London street names. So what changed? If the brain has always been this capable, why did humans bother building physical roads at all, once they had internal ones that worked? The real answer underneath the obvious one, is this. Internal maps don't scale. A single skilled navigator can memorize an extraordinary route. What a memorized route can't do is transfer perfectly at zero cost to a stranger, a child, a trade caravan of 80 people who've never made the journey before, or an army that needs to move 10,000 soldiers in the same direction without each one individually apprenticing under a master wayfinder for years first. Physical roads, and the infrastructure built alongside them, solved a problem that memory alone never could. They made expertise transferable. A cut-stone path, a worn trail, a milestone marker. All of it exists to compress decades of one person's hard-won spatial knowledge into something a total stranger can use on their very first day. That's genuinely what a road is, once you strip away the asphalt and the traffic lights. Not just dirt or stone shaped into a line, a physical container for inherited knowledge, built so the next generation doesn't have to relearn everything from zero. Think about what that actually cost and what it actually bought, because both sides of that trade are easy to miss when you're standing on top of the finished result. Before physical roads existed at any scale, becoming a skilled long-distance traveler was a multi-year apprenticeship, passed person to person, exactly like the Aboriginal songline carriers or the Pacific navigators who spent childhoods memorizing star positions under a master navigator's direct supervision. That knowledge was precious specifically because it was scarce. A community's ability to trade, to migrate away from a failing environment, to reach allies in a crisis, often depended on the survival of one or two individuals who happened to carry an accurate mental map in their heads. Lose that person to disease, conflict, or simple bad luck, and in some documented cases anthropologists have studied. Entire trade relationships or migration routes were lost for a generation, sometimes permanently, until someone rebuilt the knowledge through trial and error all over again. A road fixes that vulnerability permanently, and that's arguably the single most underrated invention in this entire story. Once a route exists as a physical, marked, maintained thing in the world, the knowledge required to use it drops to nearly nothing. You don't need a mentor. You don't need years of star charts memorized under threat of death by exposure. You need eyes, and the ability to follow a line someone else already decided was safe. That's an almost unbelievable transfer of power, from a small number of specialists to an entire population. And it's the exact same transfer of power that's still happening today. Every time a piece of software takes something that used to require years of trained expertise and compresses it down into something a total beginner can use competently on their very first try. But where does that trade actually show up first in the physical record? Which brings the story to something people rarely think about at all: trade. Long-distance trade existed for tens of thousands of years before anything resembling a formal road did, and the evidence for it is almost unreasonably well preserved. In 2018, a team led by geochemist Ellery Fromm, then at Yale University, published sourcing analysis on obsidian tools recovered from sites in Kenya's Rift Valley dating back roughly 200,000 years, using geochemical fingerprinting, matching trace element signatures in the volcanic glass to the specific volcanic source it came from. Fromm's team traced some of the obsidian back to quarries located over 25 kilometers away, and other analyses across similar East African sites have traced material moving distances exceeding 100 kilometers, well before Homo sapiens had developed anything resembling settled agriculture. That means humans were moving valuable materials across serious distances, either by direct travel or through chains of trade partners passing objects hand to hand across tribal and linguistic boundaries 200,000 years before the wheel existed, using nothing but memorized routes, seasonal river crossings, and mountain passes learned from watching older members of the group navigate the same terrain year after year. Everyone assumes ancient trade needed infrastructure first, that roads came, and then trade followed along them, the way modern people assume commerce follows highways today. The truth runs in the opposite direction almost every single time it's been studied. Trade routes came first, worn into the landscape purely through repeated use by traders who had every incentive in the world to remember the fastest, safest way to move goods. Roads, when they eventually got built, were usually just governments formalizing and paving a path that merchants, herders, and messengers had already been walking for centuries, sometimes millennia, before any ruler thought to lay the first stone. There's an even more literal version of this pattern still visible on university campuses and public parks today, and it's called a desire path, an unofficial trail worn into grass by repeated foot traffic, cutting the corner that the paved official sidewalk failed to account for. Landscape architects have studied this phenomenon closely enough that some universities, including the University of California, Berkeley, and Michigan State University, have documented deliberately waiting a full year after opening a new building before pouring permanent walkways, letting students walk wherever their feet actually wanted to go first, then paving exactly that pattern afterward. It's the same principle Rome eventually applied to prehistoric British trackways, playing out on a much smaller, much faster timescale. The human instinct to find and reuse the most efficient line across open ground didn't go anywhere. It's still running, quietly, under the feet of anyone crossing a lawn, instead of walking around it. There's a genuinely strange piece of evidence for this hiding in plain sight, right under some modern cities. In 2014, researchers working on transportation history in the UK, drawing on earlier work by geographer Alan Everett in the 1970s, pointed out that a significant number of modern British roads, including sections of what are now major A roads, sit directly on top of routes first established as prehistoric trackways, later adopted and paved by the Romans, later widened by medieval traders, later paved again with tarmac in the 20th century. The physical route, in some documented cases, hasn't fundamentally changed direction in over 4,000 years. Different surface, different century, different empire entirely. Same line across the same landscape, because whoever walked it first, thousands of years ago, had already found the one route that made the most physical sense, around the hill, not over it, above the floodline, not below it. That's worth sitting with for a second, because it means some of the asphalt under a modern commuter's tires is, geometrically speaking, tracing the exact decision a person made walking on foot, in leather sandals or bare feet, 4,000 years before Rome existed. But did every ancient landscape offer a route that forgiving? Not remotely. There's a comparable story in the deserts of the Arabian Peninsula, and it involves a scale of distance that's easy to state and genuinely difficult to picture. Bedouin trade networks, moving frankincense and myrrh from southern Arabia toward Mediterranean markets, relied on established caravan routes that predate any formal road by well over 1,000 years. Archaeologist Michael Petraglia, working with colleagues on Arabian route mapping published through the Max Planck Institute in 2011, used satellite imagery to trace ancient trackways still visible across the desert floor, routes worn so deeply into gravel plains by repeated camel traffic that the compaction remains detectable from space, millennia after the last caravan used them. Some of these documented incense routes ran for over 2,000 kilometers, from modern-day Oman up through the Arabian interior to the Mediterranean coast, crossing terrain with almost no permanent landmarks beyond the wells themselves. And the wells were the entire system. Caravans couldn't choose their route freely because the route was dictated entirely by where water existed and how far a loaded camel could travel between one well and the next. Typically estimated by archaeologists studying caravan logistics at somewhere between 25 and 40 kilometers a day, depending on load and season. Miss a well by even a few kilometers in the wrong direction, in temperatures that can exceed 45 degrees Celsius, and there usually wasn't a second chance. The road, in this case, wasn't a line at all. It was a sequence of survival checkpoints, and the empty space between them didn't matter, as long as you hit every single one in the correct order. That's a fundamentally different way of thinking about a route than the one most people carry around today, where a road is assumed to be continuous, paved, and equally usable at every single point along its length. An ancient desert route wasn't like that. It was less like a line and more like a chain, only as strong and only as safe as its weakest, driest link. A strikingly similar logic shows up in an entirely different climate, on the opposite side of the world, among people who never had any contact with Bedouin traders at all. Norse sailors navigating the North Atlantic between roughly 800 and 1000 C, the era of Viking expansion into Iceland, Greenland, and eventually the coast of North America, faced a problem the desert caravans never had to solve: near total absence of fixed landmarks, on open water, sometimes for weeks at a stretch, in a region where cloud cover can obscure the sun for days at a time. Norse sagas, along with archaeological finds including a fragment of a light polarizing crystal recovered from a 16th century English shipwreck, and analyzed in a widely cited 2011 study led by physicist Guy Ropars at the University of Rennes, have fueled decades of research into what's popularly called the sunstone, a crystal, likely Iceland spar, capable of detecting the polarization pattern of sunlight even through heavy overcast, allowing a navigator to locate the sun's position within a few degrees on a day when it's otherwise completely invisible. Ropars' team demonstrated experimentally that the technique works, locating the sun's azimuth to within about 1 degree of accuracy under cloudy sky conditions using calcite crystal and the naked eye alone. Whether the Norse actually used this specific method remains genuinely debated among archaeologists. It's one of the honest, open questions in the field, not a settled fact. But the underlying problem it would have solved was completely real and completely unforgiving. A Viking longship crossing from Norway to Iceland, roughly 1,000 kilometers of open ocean, had no coastline to hug and no star chart usable during 18 hours of Arctic summer daylight. Whatever method they actually used, they solved it well enough that Norse settlements reached Iceland by around 870 C, Greenland by 985 C, and the coast of Newfoundland, confirmed archaeologically at Loance Ox Meadows, excavated by Helga and Anstein Ingstad starting in 1960, by roughly 1000 C. So here's another reset worth pausing on. If the earliest paths were this well optimized, purely through trial, error, and death, because getting the route wrong could genuinely kill you, how did people avoid getting fatally, permanently lost in the meantime, before those optimized routes existed at all? Before there was a path to inherit? Part of the answer might involve a sense modern people don't consciously believe they even have. In 2019, geophysicist Joseph Kirschvink and colleagues at the California Institute of Technology published a study in the Journal of Neuro, documenting measurable changes in human brainwave activity, specifically a drop in alpha wave amplitude, a pattern generally associated with the brain actively processing new sensory information when test subjects sat in a dark, isolated chamber and had the surrounding magnetic field artificially rotated around them, without their conscious awareness that anything had changed at all. Subjects couldn't verbally identify which direction the field had moved. Their brains, measured directly through EEG, responded to it anyway, consistently across repeated trials. This doesn't mean humans navigate primarily using magnetoreception the way some migratory birds and sea turtles demonstrably do. Kirschvink and his colleagues are careful to describe the finding as preliminary evidence of a vestigial or subconscious sense, not a controllable internal compass anyone can consciously use to navigate. But it raises a genuinely open question that current research hasn't settled. How much of what felt like instinct or a good sense of direction to ancient travelers may have included a biological input modern people have never been taught to notice? Because modern life has never once required them to. Everyone assumes a sense either obviously exists, you can feel it working, or it doesn't exist at all. The truth, based on this research, sits somewhere far stranger in between. A sense your brain may be quietly using right now, every single day, that you've never once consciously felt, and that no ancient navigator ever needed to explain. Because they never had reason to doubt that their own sense of direction was simply a normal part of being a person moving through the world. The answer involves something most people have never heard of, and it might be the single most quietly impressive survival skill in the entire story. Environmental literacy at a level modern life has almost completely erased. Traditional Inuit navigators across the Arctic developed and relied on a wayfinding technique using what are called sastrugi, wind-carved ridges in snow that form with an almost shockingly consistent orientation relative to the prevailing wind direction across a given region. Anthropologist Claudio Aporta, publishing extensively on Inuit spatial cognition through the 2000s and 2010s, based on fieldwork across Nunavut, documented how experienced Inuit travelers could read sastrugi patterns to maintain a consistent heading across completely featureless, flat sea ice terrain with no landmarks whatsoever, in conditions of low visibility or total whiteout, where a compass, if you had one, could become genuinely unreliable this close to the magnetic pole. Aporta's research recorded elder navigators successfully maintaining accurate direction across distances of over 100 kilometers of open sea ice, using nothing but the angle of snow ridges under their sled runners, reading the ground itself, essentially like Braille, in conditions where a modern hiker with a smartphone compass and a satellite view would be in genuine, immediate danger. There's one more piece of evidence worth including here, because it complicates the picture in a useful way. It suggests that reading the landscape wasn't a separate skill from tracking animals through it. In many communities it was, and in a few remaining places still is, the same skill entirely. Cognitive scientist Louis Liebenberg has spent decades documenting the tracking abilities of sand hunter trackers in the Kalahari Desert, publishing extensively through the 1990s and 2000s on what he calls persistence hunting and the interpretive skill involved in it. Experienced sand trackers can identify an individual animal from its footprint alone, not just the species, but frequently the specific animal, based on subtle variations in gait, weight distribution, and old injuries visible in the print pattern, while simultaneously reconstructing a timeline of when the animal passed, based on factors including how wind and sun exposure have altered the edges of the print. Liebenberg has argued, in work published through the South African Archaeological Bulletin and later expanded in his book on the subject, that this kind of tracking may represent one of the earliest forms of systematic scientific reasoning practiced by humans, forming a hypothesis about an animal's location and behavior, testing it against physical evidence, and revising the hypothesis as new signs appear. The relevant detail for the story of the road specifically is this: sand trackers don't just follow an animal's trail, they predict where it's going to be, based on terrain, water sources, and time of day, meaning the path they follow often isn't the literal trail of footprints at all, but a mental route constructed by understanding the landscape well enough to know where any given animal would logically choose to go next. That's not navigation in the sense of following a line. That's navigation by understanding the reasoning of something else moving through the same space, a kind of route finding that has no simple equivalent anywhere in a modern navigation app. Here's a twist worth sitting with. Modern people tend to assume that technology has made humans better navigators than our ancestors ever were. In one narrow, specific sense, precision, when the technology is working, that's true. But research on modern navigational dependency tells a more uncomfortable story. A 2020 study published in the journal Scientific Reports, led by cognitive scientist Luisa Damani at McGill University, found that habitual, long-term GPS use was associated with reduced hippocampal spatial memory function on independent, unaided navigation tasks, meaning heavy reliance on GPS may actively be causing the same brain structure that Eleanor Maguire found enlarged in London taxi drivers to functionally shrink, or at minimum, underperform, in everyday users. Put plainly, the very organ that let a Polynesian navigator cross open ocean using nothing but stars, that let an Inuit hunter read wind patterns in snow with pinpoint accuracy, that let an Aboriginal Australian carry a 1,000-kilometer route inside a song, that organ is still sitting inside every single skull alive today. It's just increasingly outsourced, increasingly unused, increasingly asked to do nothing more demanding than confirm that the blue dot on a screen is moving in roughly the correct direction. So, what actually happened to all of that ancient capability? It didn't disappear. It got replaced, layer by layer, by systems built to be so reliable that the underlying skill never has to be exercised at all. That replacement has a surprisingly precise timeline, and it's worth walking through the milestones directly, because each one represents a moment when humanity chose external infrastructure over internal memory, one piece at a time. The magnetic compass, first clearly documented for navigational use in Chinese texts from the Song dynasty around 1040 C, specifically referenced in a military manual called the Wujing Zongyao, gave sailors a stable heading reference independent of stars, meaning navigation could continue through overcast skies for the first time in human history. Before that single invention, a run of consecutive cloudy nights at sea could mean genuine, life-threatening disorientation for even the most experienced sailor alive. The mechanical odometer, described in principle by the Roman engineer Vitruvius around 27 BC and later refined across multiple cultures, let travelers measure distance traveled with reasonable precision for what may be the first time in history, rather than relying purely on estimated travel time. Milestones themselves, literal carved stone markers placed along Roman roads at intervals of 1 Roman mile, about 1,480 meters, gave ordinary travelers, for the first time in the historical record, a completely externalized, standardized way to know exactly how far they'd come and exactly how far remained, with zero personal expertise required. You didn't need to be a trained navigator anymore. You just needed to be able to count. So where did all of that eventually lead? And then, in 1978, the United States launched the first prototype satellite in what would eventually become the Global Positioning System, a network that, by the time it reached full operational capability in 1995, could locate a receiver's position anywhere on Earth to within a few meters, using signals bounced from satellites orbiting roughly 20,200 kilometers overhead. 20,000 kilometers. That's the distance between a modern smartphone and the satellite doing the navigational work a Polynesian master navigator once did entirely inside his own memorized understanding of stars, swells, and seabirds. There's a strange symmetry buried in that number if you're willing to sit with it. Modern GPS accuracy for a standard consumer device is generally accurate to somewhere between 3 and 5 meters under open sky, according to figures published by the U.S. government's official GPS. GovResource, Mau Piailug, using nothing but memory, was landing double-hulled canoes on Pacific Islands after multi-week voyages with an error margin, by most accounts of his documented voyages, of well under a mile. Neither system is meaningfully better than the other at the actual job. They're just radically different in one crucial respect. One of them lives in a satellite that took a global superpower and billions of dollars to put into orbit, and the other lived entirely inside a single human skull, transferable only by decades of direct teaching from one navigator to the next. Everyone assumes this progression is a simple story of improvement, worse tools replaced by better ones, in a straight, uncomplicated line toward convenience. The truth is more complicated and considerably less flattering. Every layer of external navigation infrastructure humans have ever built, the compass, the milestone, the paved road, the satellite, has made human wayfinding faster, safer, and more reliable. And every single one of those same layers has also, measurably, made human beings individually worse at doing what their own brains evolved over hundreds of thousands of years to do without any outside help at all. That's not a criticism. It's closer to a trade, arguably one of the best trades humanity has ever made. When you weigh a few meters of unused hippocampal gray matter against several billion people no longer routinely dying of exposure while lost in unfamiliar terrain. But it is a trade. Nothing about modern convenience was free. It was purchased, slowly, gradually, across thousands of years, in a currency ancient humans never had to spend, because they never had the option, skill they didn't have to develop. So think again about that person standing at the edge of the forest with no path in front of them from the very start of this. It's tempting to imagine them as hopelessly lost, a person in genuine danger, purely because there's no line drawn on the ground to guide them. But that framing gets the ancient reality almost exactly backwards. That person wasn't lost at all. They were reading wind direction, star position. The angle sunlight was hitting a specific rock formation, the behavior of birds circling in the middle distance, which almost always means water nearby, the compacted soil of a game trail that a herd had been reinforcing for generations before that person was even born. To modern eyes, dropped into that same forest with no signal on a phone, it would look like nothing. Undifferentiated trees, in every direction indistinguishable from each other, to someone raised inside that environment. Spending years developing exactly the kind of spatial cognition Eleanor Maguire found physically altering brain structure in London's taxi drivers, it was never blank at all. It was already, in every meaningful sense, a road. It simply wasn't a road anyone else could see yet. The real answer beneath the obvious one, the one hiding underneath every songline, every star chart, every game trail worn smooth by 6,000 pounds of elephant repeated across centuries, is this. Humans didn't wait for roads to move through the world. Humans were the road, long before anyone poured the first mile of pavement, carrying the route inside memory, inside song, inside a hippocampus, quietly building a map cell by cell with every single journey. The pavement came later. It always does. It's simply easier to notice, because it's the only part of the story that was ever built to be seen. You're standing at the edge of that same forest again, except now you know something the person in the opening scene already understood instinctively, and something most people alive today have almost entirely forgotten how to access. There was never actually a version of humanity without a road. There was only a long, patient stretch of history when the road lived inside a person, instead of underneath their feet. We didn't invent the ability to find our way. We just eventually built something we could stop having to remember.